Hi, my name is Alex Perkins, and this is my final project for computer vision called Face-Anchored Augmented Reality using Monocular Distance Estimation. Earlier in this course, we built an augmented reality demo that anchored a virtual object to a checkerboard pattern or a physical marker. That approach used a still inanimate object, which always needed to be in view or frame, and I thought, could we just shift it to a moving or live object like a face? So for this project, I tried exactly that. A person's face instead of a board or a pattern on a flat surface. This means no markers needed at all, and it works with a single uncalibrated camera. I built this by extending the real-time facial detection from Project 1 and merged it with Project 4's AR pipelines we explored earlier in this course. When it comes to detecting a face, the pipeline starts with a Haar cascade classifier. This is the Viola and Jones algorithm, which detects a face within a box frame. When it comes to distance, a face that looks wider in the image is closer to the camera, and a face that looks narrower is farther away. That's just how perspective works. And it's the same principle you'd use to judge distance with your own eyes. So I turned that into a formula to use for this project. Distance equals some assumed average width for the face in centimeters, so in this case 14 centimeters, times the camera's focal length, divided by the frame's width for the detected face in pixels. Since I don't have a calibrated focal length for this camera, I am using a webcam, I approximated it as equaling to the image width in pixels. Once the distance is estimated, I can project the face's 2D position into an actual 3D point in front of the camera, using the pinhole camera model, which was used for camera calibration and augmented reality early in this course. From there, I built a small library of 3D objects, a birthday hat, a crown, a halo, and a pair of glasses, as well as testing a pyramid to begin with, each defined as a set of vertices and faces in a real-world centimeters. Each object gets anchored to that 3D point, which with a small offset so that it sits in a sensible place, either on eye level for the sunglasses or on or above the head for other objects like the hat or the crown. Everything was projected into the live video with OpenCV's project points function. So after testing various objects anchored to the face, there were two more tests that I was looking to try out. First, to see if more than one face can be detected and applied objects to them at the same time. I confirmed this by having my trusty volunteer or another person next to me in the frame, and the system correctly rendered two independent objects, one per detected face. The second test was to test distance accuracy. When I first measured out a distance just simply using a tape measure from my webcam to my face, it was around 76 centimeters or 30 inches from the camera, and recorded what the system estimated across 76 frames while cycling through the different objects. I found that the average came out to be 55 centimeters, or specifically 54.8. That's quite a difference. We're talking about an underestimation by about 28%. So additionally, since the readings were so tightly clustered, that's not random noise. It's a consistent, systematic bias. That points to my assumptions. The average facial width and the approximated focal length do not match my actual face and the camera. And further testing and looking at these objects at different angles, there was another finding during the test, which reflected a limitation. When I turned my head to the side, the object didn't stay put on top of my head. Instead, it drifted forward away from my forehead. So you can kind of see that in these pictures, is that clearly here with the crown, when I'm facing forward, it sits right on top of my forehead. But when I turned to the side, it started sliding down away from the rest of the top of my head. Now, this happens because the system anchors everything to the center of the facial detection box. And that box itself is basically shifting as the face turns. So the detection fits, or the overall rectangular box changes with the head angle. This is known, or a known limitation of frontal face detectors like Viola-Jones and Rowley neural network detector I cited in my reports related work. They're both built and tested on upright forward-facing faces. So as far as the takeaways or the conclusion from all this, I had to take a step back and really just look at what my approach used, and that was a simple geometric formula, where the accuracy is only as good as my assumptions about the facial width and the focal length, like for example, the 14 centimeters. Unlike a learned approach, which could adapt, but would have its own different limitations. The rotation issue connects to a bigger idea found in a visual SLAM survey from one of our previous readings. The SLAM systems solve this kind of drift with persistent tracking across frames, but that's a much more complex pipeline than what was built here. If I extended this project, the natural next step would be maybe facial landmarks, tracking the eyes, nose, instead of just a bounding box around the face. So that should give a much more stable anchor as the head turns. And measuring my actual face or facial width and this camera's real focal length instead of using a generic assumed values. So that would help likely close a lot of that 28% gap.